So far, our work has taken place in what we call the real number system. We now extend the real numbers to a larger system known as the complex number system. We do this by defining a single number denoted lowercase I, and we set that equal to the square root of -1. We call this the imaginary unit, and the lowercase I stands for imaginary. It is important to note that we call it imaginary for historical reasons. It is likely that you have technology in your pocket right now that was engineered using complex and imaginary numbers. So don't discount these as being not important. The complex and imaginary numbers very much have grounding in the real world. We extend the real numbers by including the imaginary unit as well as all numbers that are sums and products of I and itself or the real numbers. This simple extension brings surprising depth to the complex numbers. We're going to work through properties that come about in the complex number system. We're going to start off with the easiest property, which is finding powers of I. So if I is equal to the square root of -1, then we can calculate I squared by thinking of it as being I times I. But I is the square root of -1, so this becomes the square root of -1 times the square root of -1. And the square root of something times itself is just going to be the thing inside the root, making this -1. So I squared is equal to -1. I cubed can be calculated by thinking of it as I squared times I. Well, we know that I squared is equal to -1. And I is just equal to I. So it simplifies to -I. I to the fourth we can think of as being I squared times I squared, but that's -1 times -1, which is 1. If we go one more to get I to the fifth, we can think of this as I to the fourth times I, but I to the fourth we already decided was 1, so I to the fifth simplifies to just being I. And in fact, this takes us back to the beginning and shows us a pattern that when we take higher powers of I, we're just going to cycle through this pattern where we get -1, -I, 1, I, -1, -I, 1, I, and so forth. We can see this visually by noting that as we multiply by another power of I, all we're going to do is progress one step through this cycle. So we just went through and showed how I is equal to the square root of -1, I squared is equal to -1, I cubed is equal to -I, and I to the fourth simplifies to 1. And if we multiply by I again, we go back to I, multiply by I again, we go to -1, -I, 1, I, -1, -I, and you just keep going around this cycle as you multiply by powers of I. This predictable cyclic pattern makes it simple for us to calculate higher powers of I. We simply use our properties of exponents to simplify a high power of I into smaller powers of I that we're familiar with. So I to the 12th could be written as I to the 4th times I to the 4th times I to the 4th. But we know that I to the 4th is equal to 1, so each one of these terms is really just a 1. So 1 times 1 times 1 is just going to be 1. What if we go even higher, I to the 43rd? Well, again, falling back on our properties of exponents, we could think of this as I to the 4th to the 10th. That would give us I to the 40th, leaving us with 3 more powers of I. Well, I to the 4th is just 1, so that's really just 1 to the 10th. And I cubed is -I, so the whole thing simplifies to -I.